Hi, these are the practice problems for Module 2, Lesson 8. Um, these first ones should be review, so I'll just do one to demonstrate. But we are comparing arithmetic and geometric sequences. So the first and fifth terms of the sequence are given. Fill in the missing numbers. If it's arithmetic, then fill in the numbers if it's a geometric. So notice at the top, we have written out arithmetic and then geometric. So to start with the arithmetic, we know we have to subtract our first and last numbers. So 48 minus 3 equals 45. And I have 1, 2, 3 jumps. Nope, 4 jumps, right? So I'm going to divide by 4, that 45 by 4, and I get 11.25. So each one I'm going to add 11.25 to. So that makes this 14.25 plus 11.25 is 25.5 plus 11.25 is 36.75. All right, let's do geometric. So geometric, very similar, except this time we're going to divide our numbers. So 48 divided by 3 gives us 16. And I still have the 1, 2, 3, 4 jumps. So 4 jumps would be a fourth root of 16, which is actually 2. So 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48. So you're going to keep doing that to finish these up here. We're going to keep going on though. All right, so these guys, we're just kind of looking at general information that we note from each of these. So answer the questions below with respect to the relationship between sequences and the larger families of functions. So we're comparing sequences with functions. Relationship is modeled with a continuous function. Which of the domain choices is a possibility? We know continuous has to involve everything in between. So it can't be natural, can't be positive integers. Those two are the same. W, we haven't really even talked about, but real numbers, doesn't matter if they're positive or negative or both, but real numbers represent continuous. 5, which of the options below is a mathematical way to represent natural numbers? Well, we know natural numbers is not represented with an R, a Q, or a Z. It is represented with an N. So it has to be the last one. Let's keep going. Number 6, only one of the choices below would likely be used for a continuous exponential model. So continuous means it has to be a explicit. So we can cross out A and D. Both of those are recursive. And we want an exponential. Well, B is the only one with an exponent. So it must be B. 7, only one of the choices below would likely be used for a continuous linear. Well, if it's continuous, we again need explicit. So that crosses out A and D. And we want linear this time. We know we need to have that multiplication. So it must be C on this one. 8, which domain choice would be most appropriate for arithmetic or geometric sequence? So we're looking at a sequence, key word here. That means it is not continuous. So that means it cannot be real numbers. Same with the Q, can't be those. So we're looking at either integers or natural numbers. Now, if we're going for the most appropriate, we don't normally start a sequence with 0. Here, the only difference between these two is the integers include 0, the natural numbers does not. So we're actually going to go with D because we usually start with the first term when we list a sequence. 9, what attributes will arithmetic or geometric sequences always have? Choose all that apply. So we're looking at between continuous and discrete. Sequences. Again, we're looking at sequences. Those are discrete. We have a number, we have the next number, we have the next number. So between domains, natural or real. If it's a sequence, we just said earlier, they have to be the natural numbers. Out of these last three, they're kind of on their own. Negative x values. We don't typically go negatives when we're doing sequences. I mean, we usually start with a first term, not with a negative fifth term. So we're not going to use that one. There's always something constant, right? We're either adding or we're subtracting. We're multiplying or we're dividing. So there's something constant in there. And our recursive rule. We always have a starting point and we always do something to get our next number. So we do have the recursive. The next two are very similar, 10 and 11. What type of sequence fits with linear mathematical models? Well, if we're looking at linear and mathematical, linear, then we want arithmetic. What is the difference between this sequence type and overarching umbrella of linear relationships? So discrete, continuous, domain, use vocab words to describe this. So sequences, I'm going to put sequences here. I'm not going to write this all out, but we'll talk about it. Sequences are always discrete. So they are discrete, whereas linear is usually continuous. Their domain is natural numbers. We have domains of natural numbers when we're talking about sequences. Linears, other linear relationships could have real numbers or anything for their domain. And what they have in common are both are straight. So if I put my dots on a graph, they go kind of in a straight pattern. Or if I'm doing a line, there it's straight. No matter what, they are straight. Okay, next one. What type of sequences fit with exponential mathematical models? Well, that would be your geometric. So now let's compare geometric with the overarching umbrella of exponential relationships. Same idea as what we've done up here with linear, except now we're talking geometric. So geometrics are the sequences are a specific type. Sequence, I'm going to try again with that one. Sequences, again, are discrete. They have the domain of natural numbers. And this time when we are talking about both are curved. So whether we're doing a line like this or we're doing the dots, they're still going to be curved as they go around. So big difference between sequences and just linear or geometric relationships in general is sequences are always a list of numbers. They're discrete. So we have a domain of natural numbers. We have a first term, a second term, a third term. We can't have a half term. And their shapes are the same as the parent relationship. All right. Now these guys, let's apply what we've been learning to here. So we want explicit equations, and then we're going to try them out. So notice here number 21 is a bonus. So we're going to put a little circle on here that's a bonus. This one we haven't really done much with, but we're going to give it a go anyway. So if I look at what's going on here, I know it's a minus 7. Here's a minus 7. Here's a minus 7. So if I'm going to write this equation, I know it's linear. F of x equals, I'm going to use the letters they give me up here. F of x equals, and I'm going to write it below, my starting number is -4. And since it's linear, I'm going to add -7. And this time I'm going to do n minus 2. Because I've started with a 2 over there, I know I have to start with the second term. So this is one way we can use directly what we find as our common difference and the starting point with what term we've gone with. Next one. What are we doing here? Well, looks like we are timesing by 5 to get rid of that 5. Yep, times by 5 times by 5. So this one is geometric. So here I'm going to put f of x, that's what they call it above, equals, well, my starting term is, oh, you know what? I have my 0 right here. Let's just use that. 2 times 5 to the x power. Oh, and you know what? I used an n over here when I should have used an x. Let's put an x over here because we can be consistent. All right. So there, I've got that one figured out. Okay, let's go over here. This one is a negative 24 to a negative 48. This one looks like a times 2, and it is a times positive 2 because I'm keeping the negative. So that means I must be timesing by positive 2. So we've got another geometric, f of x equals, I don't have a 0 here, so I'm going to go back with what I did on this first one and just do my starting term of negative 24 times 2, because that's what I'm repeating over and over. And then here we're going to do to the x minus 2, because I've done the second term. So I need to do the x minus 2. All right, last one. Here it looks like we are dividing by 3 each time. So that's a times 1/3 times 1/3 times 1/3. So that is a geometric. So I'm going to do f of x. Again, I'm going to use whatever term they've given me. But notice these are negative. So let's see how this affects it. My starting term is 81 times 1/3. Now, normally I'd put x minus whatever number I've started with. Well, because it's not writing for me. Get that cleaned up. So x minus a negative 4 is really the same thing as an x plus 4. Because really my goal is to get this to a 0 so that no matter what I'm multiplying 1/3 by, it gives me a 1. 81 times 1 to get my first number. So negative 4 plus 4 would make it, I'll write that better. This is kind of a unique one. I want to make sure you can see it. X plus 4. There we go. So I've got to get that to the 0. So negative 4 plus 4 puts it a 0. 1/3 to the 0 is 1. 81 times 1 is 81. So I've got that one. All right, let's scroll up a little bit. Here, let's look at our equations here. So now it's a line. So I know I need a slope. I need an m. I'm going to do that. Let's do an m. And I need a b, right? Y equals mx plus b. Well, my b, it looks like, is right here. So that's 2, positive 2. And my slope, if I'm looking at it, looks like I'm going over 3 and down 1. So that'd be rise of 1 and a run of 3, and it's negative. So if I put that in my y equals mx plus b form, it's negative 1/3 x plus 2. All right, let's jump over here to the geometric one. So the geometric, I need 2 points. So I have a 0 and 1. And my next point is 1, 1, 2, 3, 4. So I know it's a times 4. So I've got my starting point and I've got my common ratio. So f of x equals, I start with 1. and I'm multiplying by 4 repeatedly. And that's that was a 0. I can just leave it like that. All right, let's go back to this one. Okay, so here I need my m. It's a linear, it's a line, and a b. Well, looks like my slope is right 1, down 1. So that would be a negative 1 over 1. And my intersection, my y-intercept is 1. So y equals m is negative 1x plus 1. All right, let's go to these. So again, I need some couple of points here. Well, I have a point here at 1, 1. And it looks like the next time it crosses is over here at 1, 2, 3, comma 1, 2, 3. 1, 1. Oh, here we go. And 2, 2. Okay. 1, 1, and 2, 2. So I see it's at times 2. I have a point of 1, 1. So I can go f of x equals, I've started at 1, 1. So we're going to put 1 times, I'm going to repeat 2 over and over. But since I'm using the first term, I need x minus 1 at the top. All right, next one. We have a y-intercept of 1, 2, 3, 4, it looks like. I can't tell on my paper very well, but m and b. So b is negative 4, and my slope looks like it's down 4, right 1. So down 4, right 1 would be a slope of negative 4, rise over run. So I'm going to do y equals m is negative 4x minus 4. Okay, so now this guy, we're going to show you a few little tricks on this, but for the most part, we know it's exponential, right? And we know we're never going to hit 2. That's the number we need to keep in mind. And here I'm going over 1 box, and here I'm going over 2 boxes. So I know there's a times 2 in here, but I also know it's going down, which means it's negative. So here's all these pieces we need to try to put together. So I'm going to do a y equals on this one. So I know it's a negative 2x. So if I put 2 to the, I'm just going to put this in here. So if I have negative 2 to the 0, I get 1 for an answer, right? There we go. That's how I get the 1 there. But let's see. Oh, negative 1. Excuse me. The negative is outside. So 2 to the 0 is negative 1, but I need to get up to positive 1. So to do that, I need to plus 2. Let's see if that works on this next one. So if I put in a 1, 2 to the first is 2. Negative 2 plus 2, does that get me 0? It does. Let's try one more. 2 to the second power is 4. Negative 4 plus 2, is that negative 2? It is. So this happens to be my equation. And notice where that plus 2 comes in. It's never going to reach 2, so that shows up as our plus or minus in this case. So that's what made that one a little bit tricky. It's not your typical exponential. So thank you for joining us, and see you next time.